Greetings, my little chemistry Padawans, my little A-level chemistry students. How are we doing? So this is the last of 6 Easter revision sessions that we're doing, or Easter skills sessions, I suppose you can call them, because we have been focusing on skills and exam technique and all those wonderful things that you guys need guidance with when before your assessments in this coming period, I suppose. Like I said, we talked about it yesterday. All of the assessments have kind of been brought forward. How that's meant to help you guys, I'm not entirely sure. But there we go. We're in this situation. Hey, Kaya. Hey, Sarah. How are we doing? Hello, people in YouTube. Make sure you say hello in the chat. I'm here with you just for the first few minutes as well. So what are we doing today? Well, we're going to look at some enthalpy and we're going to look at some thermochemistry or thermodynamics. Okay, so we're going to go right through. We can see all the links going from AS all the way through to the A-level stuff in terms of Born-Haber cycles and lattice enthalpy and entropy and feasibility of reactions and all that sort of stuff. So there's a PDF. Okay, the PDF in YouTube, as usual, is in the description. The PDF for TT members is on the page underneath the Join Live Class button. Okay, so you can find that PDF there. I've selected a bunch of different questions from the 3 major exam boards, AQA, OCR, and EdXL. So I mixed it up a little bit. But what I've done here, and that's why I've called it classic enthalpy questions, is because they are classic questions. Okay, you're going to get obviously slight deviations of these worded in a slightly different way and so on and so forth, but these kind of typify the most important skills that you need to have if you're going to attack these enthalpy thermodynamics questions correctly. Okay, so what we're doing today isn't just, okay, let's just sit and watch Rich answer some questions. Okay, we're going to talk about how to attack these questions. We're going to talk about what sort of information we need, how we present that information, how we present our answers. So it's all about exam technique today. Okay, so what I'm doing here is I'm going to teach you how to attack them, and then therefore when you see another question, you're going to feel more comfortable on how to attack it, just like we did in the buffer calculations one. Okay. So who else we got in the chat? Hey, ML in YouTube. Who else we got? Megan, Ellen, Imran, Michelle. We're only being assessed on AS enthalpy in our mocks. Nice. Okay. So once you've done all the thermodynamics in year 13, the enthalpy stuff from AS seems that a little bit easier, doesn't it? Okay. Just like that jump from GCSE to A level. Once you've done some A level, you're like, GCSE chemistry wasn't so bad. So, hindsight's a wonderful thing, which is why it's so important. I would highlight this to any AS students watching is, okay, there's no rush to finish the content right now. But what I would say is over the summer, just keep in touch with it. Okay. And we'll probably do something, at the end of the school year before the summer for AS students to say, right, if you're going to do anything over the summer, which we recommend you do. I know it's been crazy at the moment. You've been studying from home and stuff like that. But I promise you, if you stay in touch with the AS and make sure you do all the AS papers and make sure you're comfortable with some key topics, then you can be successful in year 13. Kaya, mine's thermo, so no AS chemistry, so no thermodynamics. But Kaya, you can't really dissociate the two because the skills from AS are transferred to year 13 enthalpy, aren't they? There's so many things in A-level chemistry from AS that transfer into A-level. Okay, you learn about equilibrium, Le Chatelier's in year 1. That's in a few different places in year 2, and you build on that and you do KP and so on and so forth. So there's those. The enthalpy, okay, the basic fundamental understanding of enthalpy. You need that clear vision of what enthalpy is. It's all about balance, isn't it, in terms of whether a reaction is exo or endothermic, bond making, bond breaking, intermolecular forces, and all that when it cuts to lattice enthalpy. So yeah, there's and that's just to name but 2, but there's loads of different things, not least your teachers when you go through to year 13 expect you to know the reactions of organic chemistry before you start your year 13 organic chemistry. Okay, so don't worry. I've done a video which we used last year. Hopefully it'll help you kind of get to grips with the major things that you need to know in order to be successful in year 13. Redox is removed, but you still get redox titration reactions. Yeah, so it's, redox titrations don't necessarily come under redox, do they, in year 13? They come under transition metals because, of course, we use a lot of transition metals in redox titrations, so like manganate, dichromate, and so on and so forth. Hey, Forrest, how are we doing? Welcome aboard. Dia had loads of redox titration questions in your last mock. Well, hopefully, you know, those titration questions that we did last week have helped you kind of get your head around those. And don't forget, I taught you the kind of, not the easy way, but your way in. Once you've got your way in, you've got your first couple of steps in your calculation under your belt, you're on the home stretch. So if you haven't watched those titration videos on our YouTube channel or in the recordings in the TT site, then I recommend you do so, because it really helped a lot of students when we were doing those. And these sessions have been really successful, actually. I've been really, really pleased. The feedback we've had for all maths, chemistry, and biology, students have found them really, really useful. So I'm really, really pleased with that. But today, it's the last one. Obviously, TT members, we will continue to do our weekly live classes over the next few weeks on the run up to your assessments and probably beyond. So just stay tuned, okay? And if you haven't already, you can try the free trial, or if you're a member of the student room, you've probably had an email offers recently about a kind of a 2-week offer. So check that out as well. There's still time, I think, in that window to kind of get involved with that. So yeah, use and abusers in a free trial. That's what we're here for, ladies and gentlemen. We're mega busy right now. We've got thousands, literally thousands of students in the course right now. So, they're all getting their extra help they need for nothing. And you guys can do the same as well. So, legends. Oh, thanks, Jay. Really appreciate that. Okay. I don't know. Maybe they'll have a plaque or something on the house. When I pass away, they'll put a blue plaque on my house and say, this is where Rich did his TT live classes from. Probably not. That's not going to happen. Right. Let's get cracking. Enthalpy, ladies and gentlemen. So PDF, as I said before, is in the description in the YouTube, and it's in the join the live class, just under the little join the live class button in your TT members page. So let's have a quick look at where we're at. Okay, so what I'm going to do now is I'm ignoring the YouTube chat, guys, to a large extent. I'll kind of like glance across every now and again if there's something major, but for the main, it's for the TT members. So make sure you've got access to the PDF, whether it's on the screen in front of you or whether you've printed it out already. Who knows? I put that up first thing this morning, so we can get cracking. So I'll just arrange myself here. Okay, so we're starting with some AS stuff. You can see here, I'm not going to give you the mark schemes for these, okay? Because like I said, we're not really here to do. We're not really here to do the questions. We're here to look at the technique and how to attack these questions. We're going to do about an hour today, okay? Because I've got a previous appointment, sadly. But you can find the mark schemes for these. They're all published to the public. So this is AQA AS Paper 2, 16, question 2. Okay, so you can always find the mark schemes for these. So we're starting with AS, and we're starting with a classic, and hence classic enthalpy questions, and that is the practical for finding the enthalpy of combustion of a fuel. So 9 times out of 10 when you get these, and they are very common, ladies and gentlemen, not just in AS papers, but also in A-level papers, they will give you the practical side of things, and there's a lot to read, okay? So what I'm going to do is suggest, has anybody got any tips in the chat here in order to maybe get your head around the question or kind of sort your data? Any tips on how to attack these? I'm just going to ask you for a kickoff. Write and highlight from Michelle. Yeah, I agree with that. Highlighting the key bits, rewording the question. That's a good idea, Megan. I like that. Label what's given. Absolutely, all really, really good ideas, okay? And things that we've mentioned before on TT Lives. So I'm going to use green because it's not as angry as red, is it? Oops. I'm going to get my pencil working. I'm just putting green dots everywhere. Blurt the keywords. Yeah. Write down all the data in the correct units that you need. That's another good one, dear. Thank you very much. Highlight numbers needed for in question. Make sure you look at the units and underline it like crazy so you don't lose the mark at the end. Yeah, I like that, Imran. Write the equation, see what you have. Read the question, then read the full question. Imran, I always do that. Look, I always do that. I look psychotic. Yeah, from what Imran said. Underline it like crazy. Yeah, just like, right. So, yes, Escher. That's one thing. A couple of you said it. read the whole thing and understand what the student is trying to achieve. It's so, so important. It's tempted to just go, oh, look at this. Blah, yeah, blah, 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 blah. Use the student's data to calculate experimental value. I mean, the thing is, there may be something just to kind of throw a bit of a curveball at you or whatever, but just read the question carefully, okay? So there's a bit of useless information. Alcohols such as methanol, ethanol, and propan-1 all are good fuels. Okay, great. Not really going to impact us. Student carried out an experiment to determine the enthalpy of combustion of methanol. Enthalpy of methanol was placed in a spirit burner and measured. The student placed 100 grams of water. So we have got 100 grams of H2O. Now, what is that? We're going to use a really famous A-level equation here. So in our equation, it is a volume, absolutely. But in our equation, which is MC delta T, what does this represent? Good, the mass, okay? So I'm just going to put M there next to it because in MC delta T, the mass isn't the mass of the fuel, okay? It's the mass of water that you're heating up. It's really, really important because all of these things link to the water. The change in temperature, 4.18 is the specific heat capacity of water. M is the mass of water. So what you're doing is you're finding out how much energy it took to heat a particular mass of water using its specific heat capacity and by how much was it heated up. So all of this is to do with the water. Never ever forget that is a big, big mistake that students make in this, is putting the mass of the fuel or something else in as the M. So we've got that done. Clamped it to the spirit burner. The burner was lit and allowed to burn for a few minutes. The flame was then extinguished and a new mass of the spirit burner found. So we've got the change in mass of the fuel here. Okay, so that's what we've got. So we can work out the difference in mass. That was the mass of fuel used. And of course, if we've got the mass of fuel used, we can find the number of moles. That's going to be our last point there. Temperature rise was 38 degrees. So delta T equals plus 38 degrees Celsius. Okay, plus 38 because it's gone up in temperature. Okay, and that's important. I'm going to explain why in a second. And we got our specific heat capacity, standard 4.18. So always use the number they give you in the question, or for some examples, it's in the data sheet. So we got a diagram of apparatus, looks like a standard one to me. We got a copper calorimeter that transfers the heat energy. So now we need to use the student's data to calculate experimental value for the enthalpy of combustion of methanol. So what I'm going to do here is, if you haven't seen it already, is just talk you through the alternative calculation for finding Q. Okay, so I'm going to write here Q equals minus MC delta T. Now, if you haven't seen the minus version before, let me talk you through it. Because at the end of the day, you need to find a delta H, okay, the enthalpy of combustion for methanol. Now, you can use MC delta T and you get a value for Q. Then you use the delta H over number of moles, and that gives you, then you use Q over number of moles to get your delta H. And then you need to just decide on whether it's a positive or negative value, okay? Imran, you're absolutely right. Using this method, it ensures you don't get the sign of enthalpy wrong at the end, okay? So we'll just work through this really quick. So Q equals minus MC delta T. So that is minus 100 because of the mass times 4.18 times 38, okay? So that's going to get you your Q, okay? So your Q here is, of course, going to be in what units? What's your Q going to be? In units, joules. Good. The reason it's joules, ladies and gentlemen, is because C is always joules per Kelvin per gram. Okay, joules per Kelvin per gram. So you're going to get your Q change in joules. Okay, so this is what is it? 15,884. Okay, and that's minus. Now, just be careful. Okay, just be careful, because if they ask you to state Q, so if the question is asking you to find Q specifically, maybe sometimes they break the questions up in stages. This isn't, okay? This is just find delta H. No matter how you get there, just find delta H. If they ask you for Q, you should always quote it as a positive value, okay? Because, you know, an amount of energy can't really be negative, can it? You either got energy or you haven't, okay? 0 is the lowest it can go. So if they do ask you for Q, don't use this minus MC delta T. But if, like here, they're asking for delta H and you're just doing it as part of your working, it's absolutely fine, okay? So we need to change that. I always do it as standard to convert it to kilojoules. That's minus 15.884 kilojoules. And that's our Q change there, okay? Good question in the chat here, okay? If the temperature is in Kelvin or degrees Celsius, it doesn't matter, because the reason is this: they work on the same scale relatively, okay? Because zero, so in degrees Celsius and Kelvin, 0 is 273 Kelvin, okay? 1 degree would be 274. 2 degrees would be 275. Now, because we're looking at a difference in temperature, a delta T, okay, it doesn't matter whether it's in degrees or Celsius. When you're just working at for a temperature, like in PV equals nRT, okay, the T in there needs to be in Kelvin, okay, needs to be in Kelvin. So if you look here, the difference, so the difference in temperature between here and here in degrees Celsius is 2. The difference here in Kelvin is 2. So because we're looking at a delta T, it really doesn't matter. Fatima, so if they ask you for the Q here, it would be plus 15.884. Yes, absolutely. So if the question was find the energy change, it has to be a positive value, or find Q, it has to be a positive value. But just because we're using it as part of the flow to get to delta H, you're not going to get marked down for it. Okay, it says in the mark schemes. So we've got our energy change Q here. Now this is the magic bit. So delta H equals Q over N. Now, because Q is a negative number, you are going to get your answer for delta H in kilojoules per mole. We're not going to go through it. We're going to get your answer for kilojoules per mole as a negative number. That minus follows all the way through. Okay, I'm using a slightly different green there. Your minus follows you all the way through, and you're going to get a minus answer for your final delta H. Now, if you are dealing with a reaction that's endothermic, you're going to get a drop in temperature. So what happens is, and I'll just show you this, Q would equal minus, let's say the mass was 100 again, times 4.18. Now, if it's endothermic, your temperature goes down. So that'll be a negative change in temperature. So let's say we went down by 14 degrees. If you put that in your calculator, these two negative signs are going to cancel out, and you're going to end up with a positive value for your Q, okay? Which then again follows you through, and you end up with a positive value for delta H, okay? So that's what we need to do here, okay? So just a word to the wise, if you want to use the minus MC delta T for this type of question, you can, okay? So long as you understand the principle of it, it's going to give you the right sign at the end regardless. The other method, at the end of the day, if you don't use the minus MC delta T and you just use MC delta T, just look at your change in temperature. If it's positive, that equals you need a negative delta H. If your delta T is negative, then you're going to be looking at a positive delta H, okay? So they're invert of each other. Ariba, yes, to find the N here, it's just mass over molar mass, okay? So we can find the change in mass here. So the mass of methanol used divided by the molar mass of methanol, that will give you the number of moles, okay? So, so that's what we need to do for these type of questions. So top tips, number one, you can highlight the parts of the question that you're going to need. You're looking for the information you're going to need. Label it with the letters of the equation that you're using. That's really handy. You can find them really easily. But like I said, read the question as a whole first, making sure, you don't just skim read it. You understand exactly what that student's doing. You can visualize it in your mind, just like, just like we did in titrations. Okay. So it's really, really important skill that. Okay. So that's that type of question there. If anybody's doing it, I'll just give you the answer. That is minus 308 kilojoules per mole is the answer here. But again, you can access the mark schemes on the TT site. Imran, sometimes I give you the data book value after this question, ask you why it's different. What would you say other than incomplete combustion or heat loss? Very good question. So there are follow-up questions to this a lot of the time, and it's about the practical, okay? And it's a classic question Imran's just mentioned there about the data book value. So your data book value is always going to be more exothermic than this one. In my top 3 reasons, okay? Number 1, heat loss. Okay, number one, heat loss. I would always go for that first, unless they say apart from heat loss, blah, 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 blah. But one is heat loss. Two is incomplete combustion. I would go for that one next if you want to write these down. Incomplete combustion of the fuel is less exothermic than complete combustion. Another one is evaporation, maybe, of the fuel. So rather than coming through the wick and burning, it's just evaporating off. So it's actually, it's counted in your loss in mass, but it doesn't actually contribute to the energy released. And lastly, the specific heat capacity of the calorimeter isn't taken into account. Now, what I mean by that, I'll say that again, the specific heat capacity of the calorimeter isn't taken into account. And what that means is that the heat energy has to get transferred through this copper calorimeter, and that absorbs heat energy. And of course, a lot of that heat energy is transferred into the water, but this is going to absorb some heat energy and get hot first and then stay hot. So there's a good proportion of that energy that stays within the copper calorimeter and doesn't get transferred into the water, okay? It's like if you turn the spirit burner off, I say turn it off, if you stop it, your copper calorimeter is still going to be hot. So that heat energy isn't in the water, is it? That's what that means, okay? So those are your top four reasons, okay? So heat loss, what did I say? Heat loss, incomplete combustion, evaporation of fuel, and the specific heat capacity of the calorimeter isn't taken into account. So they're your major ones. So these do come usually kind of associated with kind of practical style questions and maybe errors and stuff like that linking to it. Every practical that you need to know, your required practicals, I always recommend this. You're going to know a few things. Number one, the method and the reasons for each step. Number two, a diagram, if indeed there's a diagram associated with it, like distillation or something like that. Number three, the calculations involved, okay? And number four, the errors, the classic errors involved in these practicals. Those are the things they ask about, okay? Those are the things they ask about. So if you do yourself a cheat sheet for each of your required practicals, you're laughing. So that's classic number one. Classic number two is Hess's law. Now, Hess's law is, of course, the states that the enthalpy change for a reaction is the same, well, it is independent of the route taken. Okay, so it doesn't matter how you get there, the overall enthalpy change is the same. So you get a classic question like this. Equation for the complete combustion of cyclohexane is shown below. So this is combustion, okay? Standard enthalpy changes of formation are in the table below. Now, there are rules here, aren't there, when you're doing these enthalpy of combustion, enthalpy of formation, Hess's law cycles or Hess's energy cycles. So what's it all about? Do we need to focus on the combustion bit here or the formation bit here? What do we think? Good. Everyone in the chat saying formation. Look at the data. It's always about the data. This is classic examiner kind of, I don't know, being tricksy, all right? Because they'll confuse you. They'll give you this equation. Now, this equation could be anything, all right? It doesn't matter what the overall equation is for the reaction, okay? They'll probably say, oh, it's an enthalpy of combustion or a formation, and then they give you different data. It doesn't matter what that is. All you're concerned with is this is just a reaction. Could be any type of reaction, okay? When deciding how to attack these, you need to look at the data. The data is king here, okay? Data is king. That's it, Kay. Yeah, you used to get so confused when you first learned these, okay? And your arrows always go wrong. That's it, because if they mention combustion, you're like, oh, arrows down for combustion, burning down. But it's not about that, is it here? This is about formation because we've got formation data. So it's always about the data. So how do I attack these? Well, my advice to you is to write out the equation again. So I'm just going to do blue for standard writing. So C6H12 plus 9O2 gives 6CO2 plus 6H2O. I'm not really bothered about the state of matter here, okay? Because all the data they give you is going to link to that. So we've got enthalpy of formation data. What does that mean? That means arrows up, and what goes in the bottom are your elements in standard state. Okay, elements in your standard state. So down here, all I'm going to do is just put carbon, hydrogen, and oxygen. I'm not even going to balance it. Okay, not even going to balance it because you don't need to once you're well practiced at this. It's not something they're going to mark you on. So we've got our delta HFs. So we know the formation because we are forming 1 mole of C6H12. That's the definition. Remember, definitions are so important when it comes to delta H's. Okay. Actually, you don't need to write the states in the box. I mean, officially, you should write 6 carbon solid. Where are we? We need 6 H2 gas and we need 9 O2 gas. Officially, that's what goes in the box at the bottom, but they don't mark you on that. Okay, they don't mark you on that. So long as your numbers are correct, then you don't need to do that. So I just put my elements in the bottom. Forming 9O2, I'm not going to put an arrow there. Why am I not going to bother putting an arrow there? Good. Yeah, it's 0. Okay. So forming a mole of oxygen from a mole of oxygen, what's the enthalpy change there? Are any bonds being broken? Are any bonds being formed? No. All right. So nothing's happening. So nothing's going there. We're forming 6 carbon dioxide and we're forming H2O. Okay. So this is going to be minus 156.3. This is going to be 6 times minus 393.5, and this is going to be 6 times minus 285.8. Okay, so sometimes, I mean, this question is asking you to find this enthalpy value here, which is why it's a classic one, because you're finding the value at the top. If they are asking you to find one of these values, if you've got that one at the top and they're asking you to find one of the values on your arrows, set this up in exactly the same way. Okay, set this up in exactly the same way. So we're all set up now. So our delta HC, which is, for this reaction, we're trying to find the delta H combustion of hexane, or cyclohexane, I should say, equals, now, I'm putting this number in first. Do I need to change it? What do I need to do with it? Does it go in as it is? What's going on? Good, it needs to be positive. The reason it needs to be positive is because that arrow is going the wrong way. We're trying to get from here to here. Okay, that arrow, it's like trying to go up a down escalator. All right, it's just going the wrong way. So what we need to do, flip reverse it. Okay, so we flip reverse it, so that becomes plus 156.3, and I'm writing in green again, and then minus 6 times 393.5. Okay, now what I've done here, let's think about this. What I've done, if you could, you're just adding these up. So you could plus 6 times minus 393.5, and that would work because you're basically just, taking it away. It's a negative value. Adding a negative value is taking it away. So let's do that. And then again, plus 6 times minus 285.8. Why did I write delta HC, not F? So I wrote delta HC here because that is what we're calculating. These are delta HF values, okay, that we're using to find the delta HC, which is this equation here, okay, because that is the complete combustion of cyclohexane. We're looking to find the enthalpy change of combustion of cyclohexane. So that's what the question's asking for. That's what Megan said, yeah? So that's why it's delta HC. And that's what can get confusing, isn't it? Okay. So all we need to do is just put those numbers in and we're going to get our delta HC. Done. If indeed we wanted one of these values, okay, one of these values, all we need to do is I would literally move this one to this side of the equation and obviously change the sign of it, which is really important. And I'd move this one over here to make it the subject, and that would be our way of finding it. So that's the way I do things. It can be a bit confusing when they want you to find just one of these values here, okay? But write it out like you're trying to figure out the main reaction at the top and then rearrange equation afterwards. I think that's just, A, it's more reliable, I think, and B, it's a lot less confusing than trying to kind of move this around and make that the one at the top. Yeah, it's just a nightmare. So what I would say is set out your numbers for your calculation like you're finding the one out at the top, like we're doing here, and then rearrange those around, okay? That would be my best advice for you there. If indeed you're having a go at this question, Do you want me to give you the answer, or are you just going to find them yourselves? I'll give you the answer. Okay, so the answer here is, come on, Rich, I need to find it. Is this the second question or the third question we're doing? Second question we're doing. That'll be minus 2510 is the answer here. Okay. Oh, minus 3919. What am I looking at then? OCR, AS. Or maybe it is. My bad. Yeah, 3919 then. My apologies. Kilojoules per mole. Okay, 3919.5. Do apologize. Okay, there I grabbed the wrong thing. But okay, so that's how I would attack those. That's my best advice for attacking these. And it's the same for if you got delta HCs, arrows go down. You can just use that same method. Next up, another classic is mean bond enthalpies. This is something you did at GCSE, ladies and gentlemen, okay? This is something you did at GCSE. So, you know, just because they're giving you slightly different equations, like different numbers, okay, presenting it in a slightly different way, the lingo is different, but the process is the same. So attacking these, I'm going to write out the equation again. In fact, oops, I'm going to move it over here. I'm going to write it really big. 2NH3 goes to N2 and 3H2. The delta HR for that is plus 92 kilojoules per mole. Okay, plus 92 kilojoules per mole. Now the table shows bond enthalpies for N triple bond N and H single bond H. Use this data together with a standard enthalpy change of reaction for the decomposition of ammonia and calculate the value in kilojoules per mole for the mean bond enthalpy of NH in ammonia. So first of all, what's going to be the sign of our answer? What does the sign have to be for our answer here? So we're looking for the mean bond enthalpy of an NH bond. Good. It's got to be positive. Okay. Our answer has to be positive because all mean bond enthalpies are given as positive values, i.e. the amount of energy it takes to break 1 mole of those bonds. Okay. So it's an endothermic thing. So even if, and there's ways to do this where you're going to end up with a negative value, and that's fine. All you need to do is just change the sign at the end because you would have inadvertently calculated the energy released when those bonds are formed. So all you need to do is just change the sign at the end, okay? So how do I do these? Well, I do these in this way. So what I say is, okay, these are bond breaking, okay, which is what we need. We're breaking these NH bonds in order to make nitrogen and hydrogen. These are bond making. So bond breaking are always going to be positive values, okay, because we're putting energy in order to break those bonds. Bond making, okay, on the other side are always going to be negative because when bonds form, they release energy. Even when intermolecular forces come into play, okay, when two molecules are attracted to each other, energy is released. So all we need to do is put our values in. Now, of course, this is what they add up to. Okay, so the balance between these positive numbers on the left and the negative numbers on the right all basically equal out or calculate out to plus 92 kilojoules per mole. So how many NH bonds have we got over here on the left-hand side, ladies and gents? 6. Good. The reason it's 6 is because we've got 2 NH3s. Okay, so I'm going to call this 6x. X being the number or the mean bond enthalpy of an NH bond. Okay, so 6 of those. So that's 6x. Over here, we've got 1 nitrogen. So that's going to be minus 944. Okay, minus 944 because we're bond making here. I've just flipped the sign of this. Okay, and also minus, we got 3H2, so that is 3 times 436. Okay, so I've just again used the balancing and I've flipped the sign because we're bond making and energy is being released. So what we can say is that plus 944, no, what did I say? Plus 992, yeah, plus 92 equals 6x minus 944 minus 3 times 436. All right. And now all we need to do, this is what I was just talking about with the previous question, is rearrange this data to make X the subject. Okay. Now, if I moved it over here and move 92 to this side, you end up with minus 6X, don't you? Because you're flipping the side of the equation that it's on. And that's going to give you a negative answer, which isn't ideal. It will give you the correct answer, but it'll just have the wrong sign on it. So for me, I'm just going to move everything over. So plus 92 plus 944 plus 3 times 436 equals 6X. And anybody got a calculator? Can I play bond breaking and bond making to every equation? Yeah, absolutely. Absolutely. When it comes to mean bond enthalpies, I would certainly use that as your focus. Okay. And sometimes with some Hess's Law questions as well. K is getting 2344. Okay, so that equals 2344 kilojoules per mole. But of course, that's 6 of them. So what do we need to do? Yeah, divide by 3, and that gives us 390.7, I think it is, plus 390.7. Put your value on it. Don't let the examiner, don't leave anything to assumption. Put a plus or minus on it. When it comes to enthalpy, you've got to have a sign in front of it. Never don't put a sign in it. Never don't put a sign in front of it. So that's kilojoules per mole. Okay. So this technique, like I said, it minimizes errors. Okay. It's methodical. It's about process, which is what we've been talking about in a few of these lives, isn't it? Having a process, having a one way of doing things that works for you. Now, this is just my way. Okay. Your teacher may have taught you a different way for many, many things. Okay. And that's what can be confusing sometimes, but you just do what works for you. So long as whatever your hit rate is in terms of your answers, that's what you need to stick to. Okay. So that's mean bond enthalpies. Next up, we have got Born-Haber cycles. So we're moving into year 13 now, okay? So Born-Haber cycles, it's again just about, thank you, Michelle, yes. It's all about understanding enthalpy change, isn't it? Okay, so the first question here is, we've got a Born-Haber cycle for the formation of magnesium oxide. All right. So the first thing we need to do is complete figure 1 by writing the missing symbols on the appropriate energy levels. Okay. So what we're looking to do here is, obviously we've got a few different things to actually complete. So we need to know, and I think the process again here is really important, right? What do we need to do to these bad boys in order to turn them into these? And it's one step at a time. Okay, so what have we got here? Let's label these up. So what's this difference here, guys? So we got from magnesium solid, half O2, to magnesium plus O gas. What is that? What's that, the delta H for? Atomization of O2. Good. So this is the delta H atomization of oxygen here. Okay. For this one, next one. So we're going from magnesium solid to magnesium gas. That is the delta H atomization of magnesium. So then what's next, guys? What's next? What would you do next? Good. Yeah, absolutely. So we need to ionize our magnesium, don't we? Okay. So we need to, so we go to Mg plus gas plus that electron plus O gas. So that will be the delta H first, i.e. of magnesium. And then of course we go to Mg2 plus gas plus 2 electrons, O gas. And that is the delta H second, i.e. of magnesium. Okay, so it's the first, then the second. They're different values, aren't they? Okay, if you had 2, let's say you needed 2 potassium, you were like K2O, all right, you'd need 2 times the first ionization energy of potassium, okay? But because there's only 1 magnesium in the formula, we're going through 2 different ionization energies. We need to take the first one, and then we need to take the second one. Again, AS stuff coming into A2. You should know all about ionization energies, okay? Now this next one here, what's that one? So going down, this is actually an exothermic process. Good. It is the first electron affinity or delta H electron affinity of oxygen. So that absorbs one electron. Mg2 plus now is the same. And we get O minus gas and still another electron. And then this one here is the second electron affinity of oxygen, where we end up with the O2 minus. Incidentally, this one is exothermic, which is why it's going down. Okay, remember going down, negative exothermic. Okay, because the oxygen atom is more stable when it brings on that first electron. But then, of course, the second one, okay, it's O, Jake. Yeah, it needs to be O because we've already atomized it. We only need one of those things. Okay, we only need one of those things. And then the second electron affinity. Okay, so if you've got a group 6 like oxygen or sulfur, watch out for those. Your second electron affinity is endothermic, okay, because they need to put them together. All right, you've got a negative O minus, and you've got an electron, which is also negative, and they're going to repel. So you need to overcome that. You need to put energy in order to mush them together, okay, to get that negative electron onto that already negative 1 minus O atom. So for the second IE, do I have to write 2 electrons? Yes, I would say, because during this process, we released 1 electron. During this process, we released another electron. So now in total, we've got 2 electrons. Okay. Then one of those electrons gets taken on by the oxygen, which is why there's only 1 electron here. And then after the second one, there's no spare electrons because we've had that complete transfer. Okay. So you've got Mg and O. You're going to release the first electron from Mg. You're going to release the second electron from Mg. Then the first electron is going to be absorbed by oxygen. The second electron is going to be absorbed by oxygen. So it's like a double step process. Okay. They don't just go from here directly to here. You release it, release the second, absorb the first, absorb the second. Okay. So good. I'm glad that makes sense. So those are the things that we need to put in there. My advice is know the definitions of all of these enthalpy changes you need to know for Born-Haber cycles right at the beginning of the thermochemistry or thermodynamics section or lattice enthalpy section, whatever it is in the TT guide for you and the content guide. Then make sure you go to that first tutorial that talks about delta H's you need to know, and it goes through all the definitions for you. And you know, when you're looking at an equation, it's like, oh, what does this equation represent? And then it's a game of spot the difference. It's like, oh, well, that's been ionized, so that must be our delta H ionization. Okay. Solutions and hydrations, they do suck, Jake. We are going to talk about those before we finish up. Time is rolling on, ladies and gentlemen. So all I'm going to do here is ask you to calculate the value for the enthalpy lattice formation, this time, of magnesium oxide. Okay. KO, can you put equations when they ask for definitions instead, because you find it easier? I think if they ask for a definition, you should write the definition. But then again, if you can write the equation, that's the definition in equation form. And the equation is the definition in equation form. So the definition says what the equation does, okay? So it's the amount of energy required, or the enthalpy change that occurs when 1 mole of electrons is absorbed by 1 mole of atoms. So that's like, you know, electron affinity, isn't it? First electron affinity. So they do marry up the equations and the definitions. Okay. So if it helps, write the equation first and then just put it in words. If in doubt, it's always 1 mole or something, isn't it? Okay. So my advice for these is, and again, we're not going to write this out, but what I would say is that, what color am I going to use? Let's go for red. Why not? Okay. What I would say, even though these don't kind of match up necessarily, okay, I would say that if we call all of this, where are we? Okay, on the left-hand side. So this journey going up here, up here, up here, up here, and then going down and then back up again. That journey there, okay, let's call that X. Okay, so all of these, and that includes inverting this arrow. Okay, so you need to invert that arrow at the bottom. So what we can see here is that all of this, and then down, and then back up again. Once we finish that journey, we end up at this place of enthalpy, this much energy being absorbed. This is all putting energy into the system, really, isn't it? We got a little bit of a glitch here because it's an O2 minus. Here. But essentially, all of that equals this. Okay, so that journey you take on the left-hand side of the Born-Haber cycle equals the single drop you get in terms of your lattice enthalpy on the right-hand side. Okay, so all you need to do is invert, and this is always your delta HF. Okay, if you invert your delta HF, all of that equals that. Okay, so what we can say, if we put this into context, is that enthalpy of formation, I've inverted that, remember. So I'd say plus 602, plus 150, plus 736, plus 1450, plus, bond dissociation enthalpy for oxygen. Let's have a look at this. What we're going to do here, let me just get rid of my scroll so you can see the wood for the trees again. What do we notice here? If I was to write the enthalpy of the bond, the bond dissociation enthalpy for oxygen, it would look like this. O2 goes to 2O. Okay, so the bond dissociation enthalpy for 1 mole of oxygen. Are we using 1 mole of oxygen here? Careful, Kaya. No, we're not using 1 mole of oxygen. We don't need 1 mole of oxygen. We need half a mole of oxygen. Okay, so we do need to divide by 2. So this is 496 divided by 2. Okay, we need to halve it. Yeah, these are the little tricky bits, aren't they? First electron affinity minus 142. Remember, we're just going on that journey, and then plus 844. Okay, and that equals the lattice formation. Okay. However, you will get what is your value going to be, positive or negative here? Formation is negative, isn't it? Because ions are coming together and they're forming the salt. Whenever bonds form, including electrostatic attractions between ions, a positive one and a negative one, they come together, energy is released. So you're going to get a positive value here, but this needs to be a negative value. So that is the little trick. Okay. So just don't forget, all of this journey here is X. That equals just that one thing on the right-hand side. If you were ever asked to find one of these, same principle applies as before. I would write it out like you're trying to find that value on the right-hand side. Okay. The lattice enthalpy of formation. Okay. But then just take that, whichever mystery value it is, let's say that's X you're trying to find, put that over there, invert the signs, and you're in. Okay, so does that make sense, guys, that little technique there? So yeah, it's bond dissociation for O2. So this is AQA. They do like putting in bond dissociation. So it's basically mean bond enthalpy. That's what it is. Okay, so just watch out for that one. Mean bond enthalpy or bond dissociation enthalpy. So in other words, how much energy it takes to break 1 mole of an O to O bond. Okay. Dissociation doesn't come up for OCRJ as far as I'm aware. Okay, as far as I can remember, I'm pretty sure it doesn't. He's like, good. Yeah, yeah, absolutely. I don't blame you. Okay, guys, I'm cautious. I want to make sure I finish on time today. So this one here, this is a classic delta G question. So we've got titanium 4 chloride, can be made from titanium 4 oxide. We've got the equation here. Some entropy data is shown in the table below. Use the equation and the data in table 3 to calculate the Gibbs free energy change for the reaction at 989 degrees. Okay, 989 degrees Celsius. Give your answer to the appropriate number of significant figures. So looking at the data here, guys, what would be appropriate? 3 significant figures? Absolutely. 3 sig figs, 3, 3, 3. All of them are 3 sig figs. So what I do at this point is down the bottom of the page, down here, I put 3 significant figures as I'm writing the question. Because that, if they say that, appropriate numbers, or tell you how many significant figures they want the answer to, there's a mark in it for you. All right. So don't wait till you get to the end. You're like, oh, remember that. Sometimes you won't. And we've all done it. Okay. And then you lose a mark. You're like, oh, that's going in the FFS journal. Right. So when you read the question, tip, put it down by your answer, even though you haven't got your answer yet. Okay. And it reminds you. So for 6 marks here, I love these types of questions because, again, they're very methodical. Okay. Oh, sorry. What was the answer to the previous question? The answer to the previous question was minus 388 kilojoules per mole. Does 0 or less mean on delta G mean it's feasible? It does indeed. Okay, it does indeed. Oh, yeah, it's negative 388 because it's a lattice formation. So when you're forming the lattice, ions are coming together, energy gets released, it's going to be negative, not least because this arrow is going down as well. Okay, so that's an exothermic reaction. Energy is being released, energy is leaving the system, isn't it? Okay, and if you want to break that lattice, dissociation, then you need to put energy in and it would be a positive value. So just be careful here. They might ask you lattice dissociation or lattice association or formation or something like that. So just be wary, you know, what sign that's going to be depending on the wording of the question. Most of the time they'll ask for formation. Okay, so with these, there's 6 marks available here. Now, of course, we've got a whole bunch of information. Now, what's our equation for delta G, guys? And that will inform us what information we need. Delta H minus T delta S, beautiful. So delta H minus T delta S. So what we're looking to do is find out whether this reaction is feasible. We need to find all of these individual things, okay? 2 things to be wary of. T must be in Kelvin, okay? T must be in Kelvin. So you're adding 273 to whatever this is, okay? It's not a delta T. Remember I said before, it doesn't matter if it's a delta T, whether it's in degrees or Kelvin, because in terms of the relative scale, they're both exactly the same in terms of delta T. This is just T. So we need to use Kelvin for this. What's the other pitfall here, guys, in terms of like numbers and units and etc.? Joules and kilojoules, absolutely. This is 99% of the time stated as kilojoules. Delta S, as we can see here, is joules per Kelvin per mole. Okay, so when we're working out delta G, you know what? It doesn't matter unless it's stated in the question, work out delta G in kilojoules per mole, or work out delta D in joules per mole. Unless they ask you specifically, it doesn't matter whether you divide this by 1,000 to make it in line with the delta H, or you can times this by 1,000 to make it in line with the delta S. Either way, you're going to get basically the same answer. It's going to be positive or negative. Okay, it doesn't matter which way you do it. So of course, how do we find delta H here? Well, it's given in the question. All right, so that's nice and easy. So that's spotted, delta H, boom. Delta S. How do we calculate delta S, ladies and gentlemen? Products minus reactants, good. So it's the sum of the entropy of the products minus the sum of the entropy of the reactants. Okay, so we just need to be very careful here when doing this. All right, so what I tend to do is I put a line down there. I focus on these first, so that'll be 2 times 198 plus what is it, TI 253. Okay, and that's the first half done, and then minus these on this side, and you're going to get your delta S. Delta S here, ladies and gentlemen, equals plus 141 joules per Kelvin per mole. So we find our delta S like that. Do you have to state the equation? No, dear. No, they wouldn't ask you to state the equation here. I think so long as you're showing that you've done it and you've used it correctly, that's fine. So, Rich, is it safe to use? We can always use K for temperature. In any situation? Not really. Let me think of a situation where you should use degrees Celsius. I mean, when you're calculating errors on a thermometer, you need to use the actual scale on a thermometer, which is degrees Celsius, not Kelvin. But yeah, I mean, most of the time, I mean, just know that if it's a delta T, you don't need to do any conversions. If it's a T, use the conversions, okay? Anytime you use T in any chemical equation, let me just rack my brain, I think, yeah, it needs to be Kelvin. Yeah, so T in PV, PV equals nRT, and T in this one, then yeah, you can use Kelvin all the time. So we've got our delta S. Boom. Last thing, temperature. That's, of course, 989 plus 273. That needs to be in there. So, of course, delta G equals delta H, which is minus 60, minus temperature, which is whatever that is. 1262. Thank you very much. And then minus joules, so it's 0.141 in kilojoules per mole. Okay, and I will get you your answer of minus 238. That's not right. Oh, times. There you go. Times. So that's minus 238. So explanation here. What would you put for your explanation, actually? So we need to use your answer to explain whether this reaction is feasible. What would we write there? Any takers? Good. Delta G is negative, or you can say less than 0. So therefore, reaction is feasible at this temperature. Okay, that's literally, I mean, I would always tend to do that anyway when calculating delta G. Make a statement. Delta G is positive, so therefore it's not feasible at this temperature. Delta G is negative, so therefore it is feasible at this temperature. You get, because if you don't, you're leaving the examiner to assume that you know that. This is your assessment. This is giving you your grade. You know, don't leave anything out on the paper, okay? So you just make sure, just make that statement, even if they don't ask you to, all right? Because that way you're proving to the examiner, I know this stuff, okay? So the other one I would remember for this, the other classic question is that find the temperature at which a reaction becomes feasible, or find the temperature at which the reaction becomes not feasible. So what's our rearrangement here to find that temperature? What's our rearrangement? Yeah, delta H over delta S. Literally, that's it. Okay, that finds you the temperature. Delta G disappears because it's 0. So when delta G hits 0, at that point, that's the point at which either, if you, depends on whether you're going up in temperature or down in temperature, doesn't it? If you're increasing the temperature or decreasing the temperature, it's either going to become feasible or it's not going to become feasible. Okay, it really depends on the balance between delta H and delta S, doesn't it? Okay, there's the videos in the content guide. I would always recommend that you go and look at those. Okay, talking about, well, if delta H is negative and delta S is negative, then, you know, or delta H is positive and delta S is negative, or if they're both positive, you know, reactions are always feasible, always unfeasible, or it depends on the combination. Okay, so go and check out that video. I highly recommend it. Okay, because you can get questions without any numbers. Okay, just saying, well, delta H is negative and delta S is negative. Does that mean it's always feasible? Does it mean it's never feasible? Right? Go and check those out. I highly recommend it. Now, lastly, guys, we love these. Delta H solution. Now, let me just say something to you with these, okay? Delta H solution. That is the enthalpy change that occurs when 1 mole of a substance dissolves in an infinite amount of water, basically. Okay, so we've got delta H solution, but how do we work it out? What is our equation for this? That's my question to you. I'll give you a few seconds to type that out. Dissociation plus total hydration from Kea. Delta lattice plus delta lattice hydration. Yep, good. Both different ways of saying the same thing. So this is delta H lattice dissociation. That's really important because, of course, when we take a solid salt like that, bit of a GCSE diagram there, maybe even key stage 3, and we dissolve it, they separate out into the positive ions and the negative ions, okay? Like so, and you got the water in between. All right, whoops. So that's what's happening. We're having to break those electrostatic attractions between ions in the solid salt. Therefore, that takes energy. So this is definitely 100% positive endothermic. You've got to break that lattice, okay? And having that vision in your head of what's going on when things dissolve is massively important. And then we've got, as you guys rightly said, your total hydration, okay? So this will be delta H hydration. Total, okay? In other words, you've got positive ions and you've got negative ions. So you need to actually make sure you use both of those. Now, delta H hydration, we need to understand what that is. When you've got an ion, I'm just picking a positive one here, and you've got a water molecule that's polar, delta positive, delta negative, you're going to get an electrostatic attraction. Same with the negative ions, you're going to get an electrostatic attraction with hydrogen ions from water, okay? Now, delta H hydration is what is the value when 1 mole of that ion is dissolved in infinite solution, okay? So it's the energy change that occurs when those bonds form. So is this going to be, are these delta H hydrations positive values or negative values? Okay, saying negative, Jay saying negative, Dia saying negative. 3 ways of saying negative there. We've got negative, neg, and then just a minus symbol. Love how Dia's being really, what's the word? Efficient with her typing there. I love that. Yes, they are negative. Okay, they are negative. Now, don't forget, you know, if you're ever confused, like, right, is this going to be positive or negative? I don't know. Again, you can always come back to, is a bond being formed here? Well, yes, it is. We're forming an electrostatic attraction. That's a bond. All bonds are basically just attractions between something positive and something negative. Are you forming it? Yes, we are. So that's why it's positive, okay? Oh, sorry, that's why it's negative. That's why it's negative, right? My mouth running away with it, okay? Yeah, I'm not taking the mic. It's hard to type on your old iPad, you're saying. That's absolutely fine. You know, it's just an observation. I don't blame you for being efficient. So yeah, these are negative, okay? Of course, when we want to do the opposite of that, it's going to be an endothermic process because we need to kind of break those electrostatic attractions between water and these ions, okay? So it's all about balance. It's all about balance. So your delta H solution, okay, when you're dissolving a salt, is a balance between, right, we need to put some energy in to break up the lattice in the first place. But then energy is released when those ions form electrostatic attractions or intermolecular forces, hydrogen bonding with water, okay? So depending on what that balance is, that has a big impact on whether it's going to be soluble or not. Because what is it about this delta H sol, guys? If it's negative or if it's positive, what can we say about the outcome of this in terms of their solubility? Negative means soluble? Absolutely, okay? So delta H, a negative delta H sol means it is likely to be soluble. This is unlikely to be soluble. Now, why have I said, why haven't I been really clear cut here? Why haven't I said they're definitely soluble, they're definitely insoluble? Good. There's other factors at play here, ladies and gentlemen. There are other factors at play. Other factors, let's just maybe go back there. Other factors maybe that we want to take into account much, maybe? Temperature is one. Entropy is another. Okay. And of course, we've got our delta H here, haven't we? Okay. So whether this is going to be a feasible reaction, a feasible, because, you know, dissolving is a reaction really, isn't it? Okay. You're getting a change in state. So what we're doing here is, you know, taking one thing of a few things that go towards dictating whether something's soluble or not, ladies and gentlemen. Okay. So that's why we say it's more likely to be soluble. So if you've got a negative delta H solution, or the more negative the delta H solution is, the more likely it is to be soluble at that temperature. And of course, obviously, the closer you get to positive and then into positive, you know, that makes it less likely. So you can get things that are soluble that have positive delta H solution, okay? Because of course, the other factors like temperature and entropy coming in and having a part to play in that. Okay, so that's why we can't say that. But anyway, for this question, again, what we're looking at here is this lattice dissociation enthalpy. So delta H lattice, notice how sneakily they've given us -2493 here. Okay, a little bit naughty. So delta H solution for this would be +2493 plus, now these are negative. Okay, they actually have given us the correct sign here. So it's plus minus 1920 and then plus minus, or 2 times minus, I should say, 364. Why have I put that sneaky little 2 in there, guys? 2Cl. Kay has already said it. I love it when you guys answer questions that I haven't already asked already. All right, so 2Cl there. And our delta H solution should be -155 kilojoules per mole. Okay, so that would be my best advice with these types of questions. And sometimes you see them, you know, shown as like a Born-Haber cycle. I just think they confuse matters when they do that. In my personal opinion, I like to stick to this. Just give me the numbers, guys. Don't mess me around with a Born-Haber cycle for like 3 values. It's just not worth it. Okay, I mean, when you get to this, then it makes sense to have it in diagrammatical form. But, you know, anyway, that's just my personal preference. You know, maybe you guys are different. Maybe you like that. That's up to you. So what I would say, Rich's final thought, is that when it comes to enthalpy, always have clear in your mind, right, bond breaking and bond making. It always helps, okay? Whether you're deciding whether it's going to be positive overall or negative overall, it's always about balance, okay? So I've given you my best advice in terms of some of the principles, excuse me, some of the rules, and some of the processes that you can go through to help you simplify what can be quite complex questions, all right? So what can be quite complex questions. And, you know, that tip of, you know, have a standard way you do the question, like you're working out the enthalpy change at the top of a Hess Is Law cycle, or you're working out delta H solution. Lay your equations out like that. And then if you're looking to find an unknown somewhere else, if that isn't the unknown you're trying to find, like delta H solution, for example, let's say you were just trying to find the hydration of one of those ions, set it out like you're trying to find delta H solution. It's familiar, it's safe, it's like a little comfort blanket. And then once you've got your numbers in, rearrange in that format and you're going to get the right answer. Okay, so that would be my advice to you. So that is the end of today, guys. I've spent an hour and 10 minutes just nonstop talking. Apologies for that. But like I said, it's more of a teaching thing than a practice thing today. Don't forget, you can also find the mark schemes for these just by looking up those questions. You can find them in the exam guide in TT as well. Thank you very much, guys. I'm glad you found it useful again. Really, really pleased. What I would say is finally, just good luck. Those of you who are sticking with us, okay, that are sticking with us throughout your assessments coming up. First of all, well, good luck to everybody, okay? Good luck to everybody. One thing I would say, thank you so much, guys. I really, really appreciate it. Thank you very much. what I would say is that after assessments, am I going to play guitar for you guys? Yeah, maybe we'll have a social and we'll have a little bit of a jam. Yeah, it might be loud. That's all I'm going to say. But Smashing Pumpkins or something maybe. So good luck with the upcoming mocks or assessments or mini assessments or mini exams or whatever your teachers are doing with you. But I'm going to say two things before you run away. Okay. Number one, good luck. Okay. And don't stress. It's easy for me to say. I know it's easy for me to say, but please don't stress. The way things are rolling this year, ladies and gentlemen, your teachers are professional. Okay, your teachers will reflect the work that you've put in, I'm sure, when it comes to giving you those grades. And because teachers are giving you those grades, and because this is, it's not even unprecedented anymore. They were doing it last year, but because they're doing that, we saw last year a record number of students go to university. I have no reason to think there will be any different this year. Okay, so keep working hard. Just know that you are probably more likely this year than ever to get the place that you want in university. I'm not saying you're going to, I'm not making any promises. Of course, I can't make that promise on your behalf, but what I would say is you are more likely to do so. That doesn't mean slack off, okay? You work hard and you get those grades. But I would also say play hard. That's the second thing. Take rest, guys, okay? Smashing the revision till 3 o'clock in the morning didn't really help anybody, okay? You've got to take breaks. Just be sensible about it. Go out and enjoy the weather. Get some fresh air. Don't just kind of sit and watch TV for like a 30-minute break or an hour's break or something like that. You've watched enough telly during lockdown. You've watched enough Netflix and Prime and whatever else is out there, okay? It is personal, Jay. Yeah, well, personal as in like, is that what you've been doing like all year? Too much anime and fan fiction. Yeah. Well, we've all done too much of something during lockdown, I'm sure. Okay. So yeah, please just look after yourselves. That is the most important thing. You are no good to anybody, and you'll certainly be no good in your exam if you're flogging yourself too hard, folks. Okay. So be kind to yourselves, look after yourselves, and give yourselves breaks. Use the TT method. Okay. And just make sure you use action hours to get that 15-minute break every 45 minutes. It works. All right. Maddie Mel, thank you very much for saying thank you. Maddie, are we going to do a session on electrochemistry? This is the end of the YouTube sessions now, guys. Okay, so we've done 6 over the last 2 weeks on different things, that requested by students, things that I know classically students struggle with, but we will be continuing our live classes for chemistry on a Wednesday at 5:30 every Wednesday from next week, okay? And we'll probably come across electrochemistry as well. So if you want in, then just join the free trial, sign up to TT, do whatever you need to do, and you can join us for those, okay? So I will see you TT members next week. Yeah, good luck with everything. And I'm so glad you found these useful, guys. I've really enjoyed doing it. And I will see you on Wednesday at 5:30 next week. All right. Take care, guys.